first about system types? What was that all about? What was the type 0 system? Was that the no pure integration? Right? Basically, that means in the transfer function, what we're going to have here, I cannot factor out S. Or whatever S is integration in cost transfers. I can't do that. What does that, what's the consequence of that say to a step into? There's a steady state error. Right? There's a steady state error. To, let's say, a step. Right? So often what we do to fix that problem is to do what? We make a PI controller, add an integrator. Then it becomes a type 1. So that means I do have a pure S. Factor out means that I'll do. What does that mean about error to step input?
Zero.
Goes to 0. Zero steady state error to a step. Okay, well, really pretty easy to do in transfer functions. You know, we have that class. A little more awkward in state space. So let's look at the system. So here's our Y, T, U, feedback, all of the states, the A matrix, solution junction. Okay, so that's my plan in state form. Well, what I'm doing is I'm assuming access all of those states, do it for this form right now. It'd be very obvious if you add observer to this. Right, so adding the feedback path for all of our controllers is what we're doing with the regulator. But we're going to put something coming into this. Input, right? Problem. Talking about that. Except I'm going to do it in this form. I'm going to call this squiggle zeta integrator. R. And we're going to compare that to where output is. And I'm going to take an error signal and integrate. So this zeta is the output of the integrator. Adding an integrator to the system should be able to make it from type 0 to type 1 system. Well, let's look at the state equations for this thing with this extra state. We've actually added a state to the system. We have our original states. That's data. So, this is X. So we have our standard state equations here. X plus B U, Y equals C X, and U will be minus K X. But we've added this thing, K1 plus Z. So we have two things, one coming from our original state, plus this extra state we've added to the system. This is an integrator. And this is R minus Y, R minus Y, or R minus CX. So if you look at these state equations, put them into the state form, the matrix form, this is 0, this is a, and these are matrices, these are scalars. This is a 0. How do we follow this so far? So we take the original system, we're adding a state with this here. So let's look at this system. As t goes to infinity, steady state, we're after steady state errors here. Means t goes off to infinity. We assume we've got it controllable, stable, everything. So we'll have, of course, x infinity, zeta infinity, u infinity, and they're all going to go to the constant. It's going to go to, if it's asymptotically stable, because they will go to constants as t goes to infinity. It also implies that these derivatives go to 0. The derivative of zeta goes to 0, which we want, because it's an error signal. Trying to drive the error to 0. And then y, I'm going to say goes to R. So I have step input, step obviously is constant. I'm going to say my output's going to go to constant also. So all of these state equations at steady state simply this. And as I say, if R is a step, then R infinity will go to Y. There's a there. Or it goes in R. Okay, jumping ahead. It goes to constant. So let's define essentially an error. So let's look at these things. So I can subtract these two state equations. One at steady state, one for a general case. And you get all of these things.
When you say like x of infinity or u infinity, is that as it goes to infinity, or is it as
Essentially the value at infinity.
Okay, so like a steady state value?
The steady state value.
Okay.
This is the steady state equations. Steady state equations. Okay. So you take all these parts to subtract, and what happens is that term drops out. So there's R infinity is equal to R. it's a step input. Right? So we don't have to keep writing all these t's minus infinities, make a definition. I'll say xe is x of t minus x infinity, zeta e, zeta e minus zeta infinity, and u e, u of t minus u infinity, right? So basically, the time value minus the steady state value. And when we do this, we'll simplify quite a bit. It's the same expression as we were. And u, that's our input to the system, is minus k, our control gain times xe. That's fine, because all we've done here with x of e versus x is reset where my origin is. I already defined my origin to be where? Steady state values. All we're doing here is, if you really think about it, is resetting the origin. Instead of necessarily going to 0, it goes to whatever the steady state value is. All right, so this is plus number 1k1. So let's define the error and we'd like that error to do what? To 0. Go to 0. So our error equation results. And if I k hat, same way I did before. Using practice. The only thing I did, I added an extra variable. This is the error. Makes sense? Good. Questions on this stuff? Now, the one thing we have to put in here is what? Disturbance. So there's another way of handling disturbance, which is mathematically quite messy, but it's very useful. I'm not going to say that today. Questions on this? Are you able to get into the lab this week? Who's not been able to get to the lab because of the other evil people who keep you out? If so, let's get the lab for you this Thursday. observer for that. And what you want to do with that is kind of like we did here in this lab code. It's nice to compare what's step input, what's the observer versus without the observer, what's the observer. See how much you change the system. Yeah.
One's not shooting.
All right. Well, last week was a mess for me. And how about lab 2 next week? Should we have time for everybody? I don't know. They say that optimal shouldn't be in there very much this week, next week, but there should be, and there is. So, tell me if there's problems with getting in the lab. Then I want to get into talking about meter quadratic regulators. And last time, school one, we only had one set up, but that was really think of